Okay, hello everyone. Thanks for tuning in. So this is the fourth ACM AI Advanced Workshop. And yeah, we're starting where we left off. So we left off in the middle of the CNN workshop, um, which was, yeah, that was what we ended off on. So we talked about like the local receptive fields and whatnot. So we're starting where we left off, and we're gonna do a few like brief review things, and then Ben and Justin are gonna talk about the rest of these CNN stuff. So first, let's go over the kind of stochastic gradient descent training loop in the code. So this was actually originally a worksheet question where we were gonna ask you guys to like write something like this, but we figured given the format that doesn't really work very well. But I think this is a helpful way for you guys to kind of understand like what an epoch is better, what the batches are, if you actually like see what's happening in the code. So let's kind of walk through this. Um, so this is just a function, right? And it'll perform stochastic gradient descent in order to update the weights and biases of the network. Okay, so let's kind of briefly review uh, a few like vocab terms, right? So we discussed last week that an epoch, we basically refer to one epoch as basically one iteration over the entire training set. So basically, every time your network has been exposed to the entire training data set one time, then that means you've completed an epoch. And usually you're going to have to perform multiple epochs because it's usually not sufficient to just go through the training data one time. You're probably not going to have converged to the local minimum of your um, cost function within one epoch. So that's why we have to go over multiple iterations of the data, right? So let's kind of go through this line by line. So first we see on the outer loop, right? We're doing this for a set amount of epochs, right? So um, whatever that value epochs is, that's the number of times we're going to loop through this, right? So, and then we just have some arbitrary functions here that they do what the name implies. So yeah, so the first thing here is we're going to shuffle the training data each time, right? It's important to shuffle the data because if you're not shuffling the data, basically the batches you're going to construct every epoch are going to be exactly the same, right? That's not very good. That's going to lead the model to be more prone to overfitting and stuff like that. So it's good to always shuffle the data before you craft your batches. It's just important that you always kind of do something so that you're not always going to have the same exact um, split of batches for every epoch, right? So we shuffle the data. And then the next line simply is just some Python syntax that is, in retrospect, not very readable now that I'm looking at it. But basically, what it does is it's not super important that you guys understand the syntax for this right now. It just uses list comprehension to basically split this data. It basically partitions the shuffled data set into our batches, right? So whatever that batch size parameter is, it's going to partition it along that. So if our batch size is 10, then we're going to split the data into, partitions of 10 training examples each. So it does exactly like what we discussed it something like this would do when you're constructing batches. So you, for each epoch, first you're shuffling the training data, then you craft your batches. Okay, now that we have our batches, now we can actually do the updates, right? So that's what those last two lines are doing at the bottom. So for each of our batches, just perform the update, right? And that makes sense, right? Because we discussed last week how you update all of the weights and biases in the network after each batch, right? So that's why you're going to be doing the update for the same amount of times as the number of batches that you actually have, right? So remember that means basically we compute those approximations of the gradients based on the partial derivatives with respect to the weights and the biases for each training sample in the batch. And then we take the accumulation and average over all of the examples in the batch. So we get that average, and then we use that average to actually update the network. And then that happens after every batch. And then once you've done all of that, you're done with one epoch, right? Then we go back to the top of this outer training loop, rinse and repeat. So that's kind of a high level breakdown of how we actually perform stochastic gradient descent. And you guys can kind of see that in the code. So I hope that was helpful. Is there anything you guys are unclear about in any of these lines of codes or code, or just like about what an epoch is, about what the batch is when we update things? I'm just asking because I recall we had some questions on Discord about stuff like this. So if you guys have questions, just go ahead and ask. But otherwise, I think we can move on. Justin?
Awesome. Okay. So just to backtrack to what we were talking about previously, we were just going over the basics of convolutional neural networks. So in place of like a formal review where we go over the slides, we thought it might be better suited to just ask you guys some questions about some of the things that we covered in the previous workshop. So let's try our best to just go through these one by one. And you guys can obviously unmute to answer or just put your ideas in the chat. So first off, what sort of tasks are convolutional neural networks best suited for? Awesome. So in the chat, I see computer vision tasks. Any other ideas? That's a great answer, by the way. Another great answer, tasks where high neural density would be too costly. So that is something that we looked into in utilizing like filters where we kind of reuse the same weights to propagate throughout like a input data source. So another great answer. Yeah, those are kind of the answers that I was looking for. So great job, you guys. So again, convolutional neural network, as in the name, its mathematical definition comes from taking two functions, applying them against each other, and seeing how their shape changes. So we can see that really prevalent within image data. So great job with that question. Moving on, considering a color image, what is the dimension of this input to a model? So let's say we have a square color image of like side length n. Could you guys give me an expression of like the dimension, either in chat or you guys can unmute? Awesome. So very quick response. So in the chat, we have n times 3. Does anyone want to kind of unmute and explain like how you got 3 from just this question?
It's the red, the green, and the blue.
Awesome. So the RGB values for our color image. Great answer. So again, we want to make a point that when we're talking about a convolutional neural network, our input is not like something, it's not like a vector, like a 1D vector. We have like a whole volume of input, and we're going to pass that through our network. And that'll play its part in when we're actually implementing and creating these models. We need to make sure that our dimensions all line up with our different matrix multiplications and just all the operations throughout. So another topic, what is a filter?
Yeah, this one's maybe not so much of a one-word answer. So if someone could like unmute and kind of discuss what the point of the filter is, how it's used, and whatnot.
It's sort of a movable frame that consists of like maybe a 9x9, which I think the example last time, of weights that goes through the entire input data.
Awesome. So just to clarify, it's like a sliding window or like a little box of weights that will just pass through our image. We'll like move it along and then take that output of all of our like matrix multiplication or our element-wise multiplication as our like convolved feature. Great answer. So in relation to that, what is a stride? And these two things are very closely correlated.
Stride is like what the local receptive field moves by. Like if it's the stride is 1, then that the filter would shift over or shift in whatever direction by 1.
Awesome answer. So again, we're going to take that local receptive field or our kernel, and we're just going to move it. If our stride is say 1, then we'll just move it 1 pixel over every time we recompute our output for our feature. Great job, guys.
Yeah, there's also one other thing we should hit on is so what is the filter actually kind of represent? If you had to explain to someone why we have filters, like what they're encoding. So can someone kind of give us an idea of what kind of information, generally speaking, is encoded by a filter, and what's the point of them from that sense?
I'm not sure if this is 100% correct, but like since like a filter is applied over like the entire image, and like each filter is like a certain size, so like 5 by 5, for example, it kind of like takes it like compresses like information about like a pixel relative to the pixels around it in a sense over like the whole image.
Yeah, that's a great answer. So you're talking in terms of dimensionality. We are technically like breaking things into like smaller dimensions. So that's a good answer. Yeah. And we're just trying to kind of get you guys thinking toward sort of like the motivation behind this, because I don't think we actually touched on the slides yet. So great job trying to tackle that question before we even get to it. So before we move on to some new material, is there anything unclear about sort of this review and like any of the material that we went over in our previous workshop? If there is, this would be the best time to go over it. Great. So if any questions come up, just put them in chat and one of the officers will address it, or we can bring it in as a group and look it over. So just moving on, we get into feature maps. What do they do? So a filter, again, like we kind of went over, it'll scan our input volume, resulting in a 2D output. So in our example where we had, say like a 28 by 28 like image. Let's say we have a filter of size 3 by 3. We'll scan that and move and convolve around our image to get our convolved feature. And that's going to be a 2D output from our image. So let's think about what we're doing when we're acting on like our input volume. So again, like we went over, the dimension of our input volume is going to be n times 3. And when we put a filter to it, we get out an area. Can anyone kind of explain why that is? Like what's the inner workings behind that operation and why we get a 2D output?
Because the filter averages the R, G, and B like outputs, and basically makes the average into the feature map.
Okay, so I wouldn't necessarily say average, but that is a good point. Like we're trying to take that dimension 3 and map it to 1. So what we'll see being done is we can have like each different channel go through a filter, and then we will put those together. But there are different ways to do that, and average is definitely one of them. So how then do we get an output volume, given that we have like, as we know now, we get like an area? How can we get a volume?
Justin, do you want to maybe clarify what you mean by output here?
Sure. So again, when we, let's go back in our slides actually. Right here. So when we're looking at this filter, we'll pass this through our image input, and then we get an output. In this case, we have a 2D image input, and then we get a 2D output, right? So if we were to try and get a volume, potentially by using like what we already have, how would we go about doing that?
Yeah, we mentioned this last week too. So if you guys recall.
Isn't it just that you apply like 3 different filters and then you combine all 3 of the feature maps?
Exactly, yeah. So if we even think about it geometrically, if we take a bunch of like 2D outputs and we stack them together, we're going to get an output volume, right? A 3D output volume. So great answer.
Yeah, so
and
just
we'll get, go ahead.
sorry, just to clarify, so the idea is that we have multiple of these filters, right? So each of these filters slash feature maps, right, as the name implies, is going to detect kind of one feature in the image, right? So in order for us to kind of have enough information to make a classification judgment, intuitively it makes sense that we're going to need more than one filter, right? So generally, like most models are going to have much more than like one filter. Like some of them will have like upwards of like 50, 60 of these filters, and then all of those, you're going to scan the image and you're just going to stack those 2D inputs on top of each other. And then that culmination is kind of what the convolutional layer output is.
Awesome. So any questions on this concept before we move on? Okay, again, if you have questions, just put them in chat. So speaking of convolutional layers, so this is kind of the crux of this architecture. So a convolutional layer will consist of multiple of these 2D outputting filters on the same input volume to map to a eventual output volume. So again, each filter is a set of weights that is, we can call it like looking for features within the input volume. And we'll kind of get into like how it's doing this and why that is. And then we can also have like a bias vector of size k being the number of filters to use. So again, if we look back to our fully connected neural network, we had like a big web of weights, and like we added on a bias to that weight to get our output that we would pass into an activation to the next layer. So it's kind of analogous to that. So just moving on, a quick visualization of like how we can kind of internalize and make sense of this filter. So say we have an image of this 2D grayscale mouse, and we're passing a filter through this mouse and trying to glean some sort of data from it, some sort of semantic meaning. So if we just zoom in on this portion of our image, we have our local receptive field here, and this is our pixel representation. So again, we have like the blank parts, like the white as 0, and then the dark parts as like numerical values. So if we look at this, we have this kind of curve, and we can also kind of see that here. And what we'll do is we'll element-wise multiply by our filter. So in this particular sense, we have a filter that kind of looks like this. And if we were to imagine like, if we were to like kind of translate this filter into an image, we kind of would expect like a little curve in this filter, right? So intuitively, if we're applying this filter to this particular portion of our image, we can see that when we multiply and sum all of this, we're going to get a quite high number. So this is going to tell us and indicate to us that, hey, like there's something in the image that kind of matches our filter. So we can kind of say like, oh, in this local part of our image, we are likely to have like this sort of structure in our image. And the thought behind a convolutional layer is that we're going to have many of these filters, all corresponding to different aspects that we can try and capture from an image. So an example of that would be, let's say like we have a filter that's trying to detect like ears within this specific example. So in our case, the ears are like kind of like little circles next to each other. So our filter would kind of look like numbers in a circle followed by another numbers in a circle, right? And when we get to a portion of the mouse that has the ears, we want our filter, when element-wise multiplied with that particular local receptive field, we want that to like give us a large number again, indicating that like, hey, we found something that in this case looks like ears. So before we move on, is there anything unclear with this? Great. So let's move into why filters help. So again, like we touched on, filters are going to reduce the total numbers of weight because we're thinking like we have a filter of weights, like a volume of weights that corresponds to like every single pixel. We're taking this same filter and we're moving it all throughout the image. So we're kind of, in a sense, reusing our weights. So if we look back to our fully connected neural network, we had like a weight corresponding to every neuron. So in this kind of analogy, if we were to have a pixel represent a neuron, we can see how computationally and memory intensive that can be to store and then multiply every pixel by its own individual weight. So by using filters, we're reducing the number of total weights we need to maintain and keep track of. So filters will allow detection of relationship between pixels, as we saw in the mouse example, where we're kind of looking for this back edge of the mouse. And filters will also look for features. So we're convolving this filter along an image and looking for like a high activation to tell us like, hey, we have like a feature that like matches with our filter. So this is important at this particular area. So when we're talking about a convolutional layer, there are some hyperparameters to keep track of. So again, just to remind you guys, hyperparameters are things that we as developers will set a priori before like getting into the nitty gritty of our model. So examples of this in convolutional layers will be the number of filters, so that K value, the stride of our filters. So again, like how much we're moving along an image, and then something called zero padding. So this would be like a binary, like do we want zero padding or we don't want zero padding? So zero padding is something that like we can append to our image, and we'll see this in the next slide. Just think of it like the motivation behind it is if we were to, let's get into the motivation when we look at the visual, but let's just look at this closed form function for our volume size. So again, we're taking like our input and then we're adding zeros to it, and we can determine like how big our volume is going to be based on this formula, where we're taking the floor of this expression and then add 1. So W corresponds to our input volume size, F is our filter size, P is like the number or how much zero padding we have, and then S is the stride. So let's get into a visual representation of this. So again, I know this is like animated and it's pretty or whatever, but let's just look at this first section for now. So this image is what we have in blue. So let's say this is our image of a mouse. And then in this particular layer, we're setting that, oh, we want to have zero padding. So we append zeros all around our image. So we're essentially padding this with zeros, hence the name. And the motivation behind adding all of these zeros around our image is that we want to kind of level the playing field for all of our pixels within our image. So if we were to consider our filter movement when we have an image without zero padding, we would start, let's go back to, actually that's not. So we would start at this corner of the blue and we'd convolve around, let's say we have a step size of 1 or a stride size of 1. We just move this about our image going through and then coming out with our output volume. But if we notice, we're going to be touching and considering like the central pixels much more times than we do the outer pixels. So we don't necessarily want this. We want to be equitable in how much we consider each pixel in determining our eventual output. So by adding zero padding, we preserve the values of our image while like allowing our filter to pass through every pixel like more times. So hopefully this concept of zero padding makes sense. I'm gonna quickly check chat before we.
Yeah, there was actually a question that I think this visualization really helps answer. Victor asked that, is there one filter per color or can you have more? I think this also really shows how we get that output volume as well. If you look at, or right now it's going through filter W0, but filter W0 has weights for not only, it's like the previous slides we showed the filters being 2D, but the filter weights are actually three-dimensional as well. We have a set of weights for each of the input volume layers, right? So if the input volume was like RGB, like the first box was R and the second one was, or second blue square was G and the third blue square was B, then we would have separate weights for all three of those layers for filter W0 and filter W1. Then we can see how when we stack the output of filter W0 and then stack with the output of filter W1, we also get an output volume with like a thickness of 2 layers. I hope that kind of helps show where like or how the dimensions kind of work, but yeah.
Paymon, do you have something to add?
No.
Okay. So again, like Ben said, if we consider our input volume, so this would be like a 7x7. We can call it like color image. So this would correspond to the red. This would correspond to the blue, and then this would correspond to the green, right? And we will have actually 2 filters in this particular example. So we have a filter W0. So as we can see in this pass, it's convolving about our input space. So we see that's going for every single like channel as well, resulting in an output volume. So again, we have a filter with its own weight volume, as well as like a bias term. And we have 2 of those. And these will all kind of come together to give us an output volume. So in this case, we have 2 filters. So the depth of our volume is going to be 2. So let's just take some time to kind of digest this model. I think this graphic kind of does a good job of illustrating this point. So if there are any questions at this point, let's kind of address this right now with the visual.
Yeah, I think this is kind of, this animation kind of encompasses literally like almost every aspect of CNNs that we've discussed so far. So it has it, you guys can see there's the stride length of 2 here in this example. You can see we have 0 padding on the images. You can see we have 3 color channels, and you can see that we have 2 filters, 2 feature maps, right? So it encompasses kind of every aspect of how we get this output volume, which is like the output of our convolutional layer. Now, one thing I think we should maybe provide a bit more intuition for 0 padding. So I'm going to pose a question to you guys. So this animation has a stride length of 2, but let's pretend for a second that we're using a stride length of 1 instead of a stride length of 2. Okay, so can someone tell me if we use a stride length of 1, only considering like one of the color channels, right? So only considering like, let's say the top one, how many times is our filter going to hit that top left pixel of the image? So not the 0, but well, the I guess it's a 0 in this case, but the top left blue one. So if you're not using 0 padding, how many times are you going to hit that pixel? And then if you are using 0 padding, how many times are you going to hit that pixel? So kind of think about how the filter moves over the image in both cases and count how many of the times is the filter going to be over that top left pixel in both cases. Okay, yeah. So that's correct. So the chat says it'll hit it 1 time without padding and 4 times if we do have padding, right? So if we don't have padding, then and we have a stride length of 1, it's in the upper left. So we're gonna hit it on the first pass, the first time we the first thing of our filter, but then we'll move to the left and then it'll by 1 pixel and then we'll no longer have that top left pixel. And then when we go down 1, we'll also no longer have that pixel, right? For the same reason as if we go to the right 1 time. But then if we add the 0 padding, now with respect to the 0 padded image, that top left pixel that's a 0 is now in the center of the filter the first time, right? And then when you move it to the left once, it'll still be in the filter. It'll be on the it'll be the leftmost pixel in the filter. And then the same thing so then it'll hit it 2 times in that direction, and then it'll also hit it 2 times for the other direction. So that's a good point.
Awesome. Thanks, Ben and Paymon. So just to move on, let's kind of get like a high level intuition for what filters are actually looking for within images. So again, it's not going to be as simple as our toy example of the mouse where we're looking for like that back edge or like some ears or like the whiskers or something. What the filters are actually going to try and detect are different textures, different patterns, different like edges or like differences within regions. So this is actually like a printout of the filters from the first layer of ImageNet, a very famous like CNN kind of like a big like primary type of CNN. So as we can see here, like you see like very kind of abstract looking features. So like a bunch of lines in particular directions. And we can see like they're all a little bit different. So the general idea is that after we kind of get all of our outputs from our filters, they'll be activated on this particular texture or pattern. And we can see like when we put all of these filters together, they can kind of give us a better sense of like what our image is actually like containing. So like for an example, like we can see like, let's say our image lights up like this filter as well as like this filter. So we can expect like somewhere in our image in a particular local receptive field, we'll see this sort of pattern, like kind of diagonal, as well as like a vertical pattern somewhere. So again, it's not as simple as like, oh, like we're looking for a nose or like, oh, we're looking for ears, but this is kind of what the computer sees. So yeah, all of these filters, again, the filters themselves, like a 2D filter, it's going to map to like a 2D output. And it's the aggregation of all of these 2D outputs that gives us like our 3D output. Just trying to address a question in chat that said, this is an input volume put into 2D, right?
Yeah, so
hopefully that answers your question.
You would imagine like in actuality, all of these filters would be like, it would be like stacked on top of each other. So it would be like a stack of them.
Yeah, another way of thinking about it is also like each of these filters are looking for a specific feature in the image, right? So if the filter is producing a 2D output, that output is sort of like a heat map of where in the image that feature exists. So if you look, if we have one of those filters with like vertical lines, then it's going to produce a heat map of where in the image do we see vertical lines, like basic vertical lines. Or if you look at the ones with colors, you see like where in the image do we see like green in the image. And then the layers after that can build off of it, and we'll see that later as well.
Yeah, I think a heat map is a great way to think about filters and just like weights in neural networks in general. It's a very, I've heard that phrase heat map used very commonly, uh, in when you discuss papers and whatnot, when you're reading about new neural network architectures and stuff like that. That phrase is used pretty often, at least colloquially.
Awesome, great analogy, Ben. Thanks. So before we move on, I just want to check and see if you guys have any questions for us. Hopefully we've been doing a good job of keeping up with them, but if you guys have any. I'd also like a general sense of how the pacing is for the workshop. So let's say like a 1 is like super slow, like we need to speed up. 2 is like just right, and then 3 is too fast. Could you guys like put in chat, or you guys can shout out to like 1, 2, 3.
Okay, so
Awesome,
people
just
people
right.
are saying 2. So yeah, I get we can just keep going. We have a lot of content to get through. So
Awesome. Okay, so we're just going to move into other layers besides the convolutional layer itself. So again, this is a big overview of our model architecture. So we just passed through the convolutional layer, and we're going to move into this thing called rayleigh. So rayleigh is a nonlinear layer, and we're going to go into what exactly rayleigh is and what about its particular shape is important for us in this context. So again, it's a nonlinear layer, and this is what rayleigh looks like. So it's kind of like a piecewise function. So we apply rayleigh to the output of convolutional layers. And just going into why we choose rayleigh other than, or like in comparison to other activation functions that we've previously seen. So if you guys remember the sigmoid, and you can follow my cursor, it kind of resembles like this kind of curvy shape. Like it has like asymptotic bounds at like 0 and 1. So if we kind of take a look at the range of derivatives that the sigmoid has, we can see that it's relatively small. So this leads to a problem called vanishing gradient. And this can best be described as like, say we have like a small range, right? If we multiply that small number by another small number, it only gets smaller, right? And we can see as we try and implement this and integrate this into very complex networks, we'll have many different layers of this activation. So when we're backpropagating, we'll take this very small derivative and apply it to our update. So we'll be essentially like multiplying a lot of small numbers together. So this can even lead to like our gradient being a 0 value. So it can lead to us not even updating our weights at all, which is obviously something we don't want if we're suboptimal. So by using the rayleigh, we have like a gradient value that is definitely larger than the sigmoid, and it's also constant on the positive domain. So again, like whereas rayleigh is has a small derivative range from 0 to 0.25, we can see from here like it's almost like 1-to-1, right? So our slope is going to be 1 here. So we can see like as we backpropagate and we look to update our weights, we'll kind of preserve the work that we did to calculate like how much a particular weight or bias contributes to our total loss. Another unique property that rayleigh has, or a good property that rayleigh has, is that it can kill the output of certain neurons. So if we imagine like getting a negative output from a particular layer or a particular neuron, when we pass it through our activation, we can see that we're going to just zero it out. So we'll effectively, like if we think of it in the graph representation again, we're like cutting the connection, cutting like the channel of like communication from our loss back to our weight or bias for that particular neuron. We're cutting that off. So we're effectively killing this neuron. And what we're doing when we do that is we're creating sparseness within our graph. So this is like a form of regularization. So we'll kind of get into that with the other layers. But just know that regularization is just making sure we're penalizing our model for being too complex. So this can kind of help with like overfitting sort of that paradigm, like the variance and bias trade-off. And we'll get into that a little later. So in the interest of time, I'm just going to move on. If you have any questions, just put them in chat. So we're going to move on to our max pooling layer. So we're passing from the rayleigh to the max pool. So pooling layers. Our objective for the pooling layer is to reduce our spatial size of our features, both in height and width. And we're trying to like downsize the amount of parameters and computation we need to use. And this is also another form of, I guess, preventing overfitting. Very like much analogous to how we use it in rayleigh. So max pooling. This is a type of pooling layer. So max is kind of like what it sounds like. We're taking the maximum value from a particular portion of our data, our input data. So if we consider like a slice of our input and we have a f by f like 2 and 2 pixels, we can see that when we use a filter size of 2 and a stride of 2, we have like 4 partitions of our image. And when we take a max pool, we're just taking the maximum value from that particular portion. So in the red portion, it's going to be 6. In the green portion, we look at 2, 4, 7, 8. We see 8 is the biggest, so we're putting 8. Similarly, we have 3 here and then 4 for the blue part. So we can see like we're downsampling our effective like data that we're using by like 75% just by this operation. Another form of pooling that we're going to look at is average pooling. So these are pretty self-explanatory. We're going to take the average value from each like filter that we look at. We also use the term filter for like this pooling step. It might be a little confusing, but just know that we just mean like a particular area of our image. So we're taking the average from an f by f section, let's call it 2 by 2 with the same stride. So if we look here, 0 plus 0 plus 2 plus 2, all divided by 4, that's going to give us 1. Sorry about that. And we can similarly do that for each of the other partitions. So again, we just went over max pooling and then average pooling. So some common practices for pooling itself. So the parameters that we're going to set, some potential like hyperparameters are going to be the filter size and the size of our stride. So if we look at filter size 2 and 2, that's kind of what we saw. We're going to have disjoint like partitions of our image space, like 2 by 2, and then we'll take either the average or the max of that particular partition. We can also have like a 3 by 3 filter with a stride of 2. So if we think about this visually, we'll expect some sort of overlap. So this has interesting interplay when we try and consider like, I guess more complex than just like a disjoint partition. And then let's talk about padding. So it's pretty uncommon to use padding within our pooling layer because we really just focus on the values of our image. So like 0 padding wouldn't really help us in that case. And in practice, max pooling usually outperforms the average pooling step. So just to illustrate that, we're going to look at the different pooling mechanisms and how they kind of act on different features and different data. So at the top, we have an illustration of the max pooling. So if we look at our image here, again, we have, I think it's flipped from our mouse example, but for the white pixels, we have like a very high value for them. So like 255 for our white portion, and then our black portion will just be 0. So if we take the max pooling of this particular thing, it doesn't matter too much what our filter and stride size are. If we like take the max of like this little corner, our max value is going to be the white part, right? 255 as opposed to 0. So we're essentially mapping like all of this information to like a white part. And that's going to happen similarly for the entire input space. So after max pooling, we just get like a blank thing. So that's not great, obviously, because we lose some information about features that might prove beneficial for our task. So in this case, like if we were to use like average pooling, we can see like if we take the average of this particular corner, we're gonna get like 0 plus 255 plus 255 plus 0, and then average that, we get 128. So it's like a grayish area for this portion. And then we do that similarly, and then we see we can kind of preserve like a diluted form of our feature in this case using average pooling. On the other hand, if we have like, if we take the negative of this input, where we have like 0 values and then they're like straddling a high value in the middle, we would like to use max pooling for this portion because we want to preserve this these values of these pixels. So if we see here, like we have 255 from like these portions here, and then we just zero out these parts because the max of 0 is going to be 0. For this average pooling, we don't really get like a great feature representation just because it gets a little diluted. As we see, like it's not strong. It's not as strong as if we were to use max pooling. So like it might not in turn play as big as a part as it should in our eventual answer for our model. So that's kind of the pros and cons for using each type of pooling. So I'm seeing the chat is going crazy. So let's move on. Pooling layer questions. I guess if we have any lingering questions, we can also address them here. So I'd like to open the floor to you guys. So let's go into what is the purpose of a pooling layer?
Yeah, and I guess so there's a lot of great things that fall along the same kind of themes for good practices and things that we want when it comes to neural networks that max pooling really helps us with. There's two particular kinds of things that max pooling does for us. And just to clarify, based on the question we got in the chat, so someone asks, is it accurate to say that you'd use average pooling if the background has the highest value color and vice versa for max pooling? So note, like just for the purposes of the visualization, it was helpful to look at kind of max pooling on some sort of just like image where we're just looking at like color values, right? But recall that when we're looking at the structure of our CNN, right? So you take your input image and then you build a convolutional output out of that. And then usually we apply max pooling to the output of our convolutional layer, right? So it's like the next step. It's not applied to the input layer. So it's applied to basically the outputs of our feature maps, right? So it's not necessarily correct to kind of refer to them as colors. It's kind of just like, remember how what Justin was talking about, how if we have kind of a high value or a high lit up neuron in one area of our feature map, that kind of indicates, okay, you probably have like this certain pattern that this feature map is looking for here. And the idea is that max pooling kind of forces you to, this is kind of a hint, what I'm about to say is kind of a hint for answering these questions. So then we'll let you guys answer these questions after I say this. So kind of what max pooling forces you to do as a neural network is it forces you to be more decisive about what you're actually considering, like a feature being there or feature not being there, right? Because if a feature is like really prominently showing up in a feature map, chances are it's going to kind of survive the strain of going through that max pooling layer and being downsampled, right? But if the feature is not very strongly apparent in your feature map, it's kind of like only sort of there, it's a lot more likely to kind of be washed away when we downsample into our feature map. So I like to think of it as it forces the network to be really confident about the assertions it's making. And like Justin talked about rayleigh, this is another form of regularization. So with that said, I'll kind of just open it up to you guys. We don't expect you guys to like get these like completely correct right off the bat. We just want to kind of stimulate some discussion.
So this is more like of a question. So you said for max pooling, it like kind of like if it's like a strong feature, like makes it stronger, or and if like it's a weak feature, it gets rid of it. So would average pooling like kind of like remove like noise, or like would that be what average pooling does?
Yeah, that is I think that's a good way of thinking about it. What do you guys think, Ben and Justin?
Yeah, so average pooling is it is like a denoising filter because well, it's taking the average. Like if you're doing a blur, a Gaussian blur, that's basically an average filter, except it's more weighted towards the center pixel. Or if you do like a box blur, that's exactly a average pooling layer, except that it has the same size as the original image. But to add on to what Paymon said, what we're basically saying is, what we're basically trying to say is that the intermediate layers, the feature maps, are going to look a lot more like the bottom image than the top image. And also, when we're looking, when we have like when we notice there's a strong feature somewhere in the image, we don't want it to like disappear, which might happen with average pooling in the bottom example. Whereas if you have a high activation for that feature where essentially it's white all over except for a small sliver, that's usually not as useful as something like the bottom, as like the bottom image.
Yeah,
I
so
don't know if
like
that's helpful.
think yeah, so to clarify what Ben said, so like think it's very common that your feature map is going to look like the bottom image, not the top image, right? Because like the feature maps detect very particular like patterns or very specific features in the image, right? So in this case, you could see that this feature map is like looking for like a diagonal line in the image, right? So if our input image had that diagonal line, then our feature map is saying, look, there's a diagonal line here. So it lights up along that diagonal, indicating that that line is there. If we do the average pooling, you can see that that output kind of just gets diluted and it's kind of like it gets washed away. So we can't really see the feature as prominently. But now when we use the max pooling, it's like it's very strongly saying like, look, there's like definitely like a white line here, right? Because it's kind of downsampling and kind of forcing the network to be like, look, like there's definitely a white line here. So it's kind of like you can think of the feature map as being like, so do you see that feature there? And then the network's like, yeah, I sort of see it. And then the max pooling is like, but do you really, really see it there? And then maybe the network's like, okay, yeah, I really, really see it there. And then you move on with it. Or maybe it's like, okay, maybe not so much. And then it kind of gets washed away.
Sorry, I don't think this is a. I don't think this shows like that. It's a filter of a diagonal image. I think that the feature map shows that, let's say whatever feature that was, if it was like a diagonal feature, then the top image where it has that dark diagonal line shows that that feature is present in the image everywhere except that diagonal
Yeah.
line. Whereas the bottom is the feature is only present in that diagonal line, but nowhere else in the image. So I just wanted to clarify that point.
That's true. That's true. That's my
Yeah,
bad.
no, that's fine. It's kind of misleading because we were just talking about like features and it looks like that.
Yeah. But it's the same kind of principle still holds.
Mm-hmm. It's exactly everything holds though.
So we
Awesome.
kind of answered this question, but let's kind of like hit on number 2 maybe more strongly. So like why is this okay and why is this maybe useful? Why is this good? Kind of following the same themes that we've been saying, like, oh, like we give up this in the CNN, but that's actually good for this reason. It's kind of the same idea that we've kind of discussed in the convolutional layers and the filters. It's kind of the same idea as that. So does anyone have an idea of what we're referring to?
Is it that it removes the number of weights that you need, so like you don't need as much like memory to do like the calculations?
Yep, that's exactly what I was looking for. So we kind of already answered the first. There were 2 things we were kind of looking for. So we kind of already answered the first one for you guys. Like it kind of forces. So the first thing we said is that it kind of really forces the network to be really decisive and confident about its answers, which is a form of regularization. And regularization is very, very beneficial for learning in neural networks in general. So recall that when we talk about learning, if a machine is learning, that kind of refers to its ability to generalize, right? So regularization is a good way to ensure that our networks are like able to generalize, which in turn, right, reduces overfitting. So that was the first point. And then you just brought up the second point of, yeah, so not only are we doing that, not only are we implementing some form of regularization, but we're also not having to hold nearly as many weights, right? We're downsampling our weights by a lot, right? So, and then you actually do this a few times throughout the CNN usually. So we're gonna look at some CNNs, some canonical and famous examples of CNN architectures later on, and you'll see that typically like what happens is you'll have like some convolutional layer, like we've discussed, and then you'll have the max pooling layer, just like we've discussed. And then what happens is that you'll build another convolutional layer off of your max pooled results, and then you'll pool that again, and you'll keep doing that. So then you see at like each step, the amount of weights becomes less and less because we continue to downsample our model. So yeah, that's exactly correct.
Awesome. So I think we can just move on from these questions. We kind of went over it. Hopefully that's clear. So we're just going to move on. Here are some more resources if any of this is kind of unclear for you guys. Just look at the graphics here, look at like someone else's explanation. It might help elucidate things. So moving on, just zooming back out into our entire network. We just finished our max pooling layer, so we're going to move into our fully connected layers and our softmax. So again, if you recall, this is all stuff that should be familiar from our regular feed-forward neural networks. So I don't know if we made this particularly clear, but let's pretend like we did last workshop. We're working on like a classification network, okay? So at the end of all of this crazy computation using convolutional layers, everything like that, max pooling, downsampling, we ultimately need a way to compute predictions for each class, right? So for vanilla neural networks, we use softmax, where softmax maps like our output vector to a probability of each class. So let's say if we were classifying animals, we have class like dog, cat, lizard, right? So we would be 46% sure that it's a dog, 34% sure it's a cat, and then 20% sure it's a lizard. So that's kind of the intuition behind a softmax. So the input vector is a element that corresponds to a class, and then we're going to output probabilities for each class. So again, convolutional layers, we end up with a output volume, right? So we got to think of how we want to convert this output into a vector so that we can make our classification through our prediction. And we do this by a familiar tool, which is the fully connected layer. So again, just to refresh you guys, a fully connected layer will have the neurons with full connections to all the activations in the previous like layer. So like it's kind of like the stuff that we had touched on from the previous workshops. So in the case of our convolutional layer or our convolutional neural network, we have an output volume, and all we're going to do is we're just going to take this volume and we're just going to flatten it into a vector, like a 1D vector, so that we can pass it through a vanilla fully connected layer. So this will work exactly the same as how we kind of went through and discussed like with the forward propagation as well as the updating through back propagation. It's all going to be the same. So for the sake of time, we're just going to move on from this. So just know we're unrolling and then we're passing through something that is tried and true.
Yeah, so just quickly to make sure that's clear. So when we say unroll, right? So that just means, so you have this box, right? And it's made of like, our box is like our volume, and it's made of like a bunch of like those neurons, right? So just imagine you're just like picking up each neuron one by one and placing them down in like a straight line, right? And then that's kind of your vectorized, kind of flattened out, unrolled set of features. And there's just like functions in libraries that will just like do this for you. You can just like call like flatten on some tensor, some 3D tensor, and it'll like flatten it out for you.
Awesome. So sorry if that wasn't clear. Again, at the end of this neural network, again, to get our output predictions, we're just going to apply our softmax activation. So that's our entire architecture for a very general CNN. So we're just going to move into some other like additional topics. So we talked a little bit about regularization. So again, we're trying to penalize our network for being too complex. And this again will help with overfitting. So we want to make sure our network is like actually solving the problem and not just memorizing patterns in the data. So at each training step, we're going to randomly zero out like a node from a previous layer. So if we're moving upward as forward in this neural network, we're going to effectively zero out like these particular nodes. So let's say we zero out this node. So we're not going to have like a wiring or like a connection from whatever is mapping into this neuron and then mapping out of it. So we reduce our like complexity and our dimensionality of, not dimensionality, but we're just not considering a particular neuron. So again, this isn't used in the testing phase. This is purely in like the training phase. So we just want to help with our overfitting. Again, that's kind of the thing that'll follow you all throughout machine learning. We want to make our predictions accurate, but we don't want to make them like super accurate, as in like they are not able to be applicable to other use cases and other sets of data. So it'll force our model to generalize across nodes. So as we see, we zero out like these particular nodes from this crazy thing to here. So it's much sparser. And we're going to have our model have to use like these different neurons, maybe not in the way that it really wants to, but we're kind of forcing its hand. And in this way, we, again, are making sure that the model is sure of its predictions in this way. So dropout works best on fully connected layers. And you guys can check these different resources to see how that kind of plays out in convolutional layers.
Yeah, so you guys can, sorry, should I go ahead?
Yeah, so again, another resource just for a general intuition for dropout. Paymon.
Yeah, so what I was gonna say, kind of, so Justin kind of is hitting on this point already, so that this idea of regularization is kind of going to follow you throughout like all machine learning, right? So you can think of that max pooling layer that we just discussed as kind of the most commonly used method of performing regularization on the output of some convolutional layer. Okay, so usually, so for example, like to prevent our convolutional layers from overfitting and to help regularize them, we kind of implement these max pooling layers. This is the kind of the analog of that, except for fully connected layers. So this is kind of how max pooling is the preferred way of regularizing convolutional layers. Dropout is kind of the preferred way in the current literature and based on our current understanding of machine learning of kind of performing regularization on fully connected layers. And there's also like these more standard forms of regularization called like L1 and L2 regularization that you guys can look into on your own time if you're interested. But they all kind of, you'll notice they're all kind of doing the same thing, where they're kind of forcing the network to be very confident and very assertive about kind of the predictions that it's making. It's basically, I like to think of it intuitively as like you're forcing the network to make a decision with less information. And by definition, that's kind of what being able to generalize means, right? Because like if I tell you like, I don't know, 40 different like characteristics of some person, it's probably pretty likely that you're going to be able to pinpoint exactly who that person is, assuming you know them. But it's going to be a lot more difficult for you to pinpoint who that exact person is if I only tell you like 10 characteristics, right? As opposed to like 40. But if you're still able to like tell me the correct answer, that means you're basically able to make much more efficient use of the information I've given you, which is a very important like kind of intuitive property of being able to generalize. So there's a lot of different intuitive ways of thinking about why this kind of paradigm of regularization helps. Believe it or not, there's not a lot of extremely rigorous mathematical proofs that you can like decisively be like, okay, like doing this will help exactly by this margin or whatnot. We actually don't, as machine learning researchers and just in general in this field, we're not actually that knowledgeable. Like the field in general is just not very knowledgeable as to the exact math and the exact uh concrete reasons for like why these things exactly help. It's just that there's a lot of very solid intuition behind, okay, this makes sense that if it's able to do this in this manner, it's probably generalizing better.
There's a lot of like also empirical evidence for it.
Yeah.
Like you try it and
Yeah.
it works well.
So yeah, it's kind of the same thing that we discussed with hyperparameters, where it's kind of very empirically deduced, where you're kind of like so we discussed with like hyperparameters how you can perform empirical tests like cross validation to kind of test what hyperparameters are best. The way these kinds of paradigms of regularization have been developed by machine learning researchers was very empirically derived, is kind of the point that I think me and Ben are trying to make here. It's kind of like people performed a lot of tests, they kind of checked out what worked, what didn't work, and then they come up with these sorts of things. And obviously there is a lot of underlying math that goes behind why these things work, but it's just, this is a, you know, a rapidly developing field, and a lot of the things we're teaching you guys haven't been around for like even a decade, so it's all like very new stuff actually. So yeah.
Just for our offline listeners, we had a question in the chat. Can dropout regularization be used on normal, fully connected neural networks? And this is definitely the case. So if we think about our full architecture for a convolutional neural network, you can think of like the convolutional part as distinct and independent of our feed-forward part. So this definitely applies to just regular vanilla neural networks.
Yeah, another way I like to think about it, kind of going exactly off of what Justin said, is like when you view them separately, you can kind of think of it as when we just only had the fully connected neural network, you're just passing the original input image into a bunch of fully connected layers, right? But then when you look at the CNN, basically what you're doing is you're taking the input, performing a bunch of manipulations on it to extract a lot of really rich and dense information from it. Basically, you're filtering out all of the crap that like we don't care about. And you're basically giving us very information rich vectors and matrices and tensors that we then pass that really information rich data into the fully connected layer. And then that it kind of intuitively then makes sense why these CNNs do a better job. And that's also another reason why like you generally don't have to just like put like thousands and thousands of hidden neurons in each hidden layer in your fully connected network at the end of your CNN, because the inputs you're passing into your fully connected layer are already like really information rich. So you don't need an extremely complicated fully connected layer at the end.
Awesome. So we're just going to move on. So now for an exclusive for this workshop track application of our theory. So our MNIST dataset, it's a large database of handwritten digits. So this is like a canonical data set that you would use to like train and test your CNN. So obviously the task at hand is to take this input of like a handwritten digit and classify it as like a 1 through 9 digit. So 60,000 images for training and then 10,000 tests. And we've seen really, really good results with CNNs on this particular problem. So one such CNN is AlexNet. So designed by this guy, and he kind of really catapulted the widespread research and use of CNN through like his contest and this application of CNN. So he's to thank for a lot of the pioneering research that is still being conducted to this day. I recommend you guys to read up on it if you have the time. So we can actually go through and deduce like all of what AlexNet is comprised of from the material from this workshop. So it's pretty simple if you look at it. We have a convolutional layer, max pooling layer. We normalize it. So again, normalizing is just we make the data a little neater to work with. Nothing like super intense. We're just normalizing. We pass it through another convolutional layer, pooling, and then this continues until we get our prediction. So this should all be familiar to you guys, and yeah, you should be ready to kind of code this up for yourself. That's kind of a joke, but yeah, hopefully we kind of equipped you with the tools to do that. So we're just gonna jump into some discussion. So that's it for the material on this workshop. Don't leave just yet because we do have a second workshop coming up. But we're just gonna move into some discussion. So this is mainly review. So let's go through the first question. Again, you can answer in chat or unmute. So why are filters used for CNN?
Let's go lightning round, guys. Let's just like, because we know you guys know these at this point. So no one, anyone. We know you guys know. Come on. Just like a quick one sentence answer.
The filters are used to identify low-level features.
Sure. Yeah.
Awesome answer.
Well, we'll take that. All right. Number 2. Intuition behind zero padding. Just like one sentence again. Like what does it help us do? What does it kind of ensure or help with?
Make sure that each node, or not node, each pixel is treated equitably.
Yeah, right. So kind of make sure our feature map or our filter kind of hits each of the neurons like roughly equal amount of time. Otherwise, the neurons in the, or I guess the pixels, I mean, in the center are going to get hit a lot more. Okay, rayleigh. We talked a lot. It was very quick, but we talked about a lot of different things that rayleigh does that makes it good as opposed to using sigmoid. And just a quick thing to add, I think rayleigh, so I think rayleigh stands for rectified linear units. Correct me if I'm wrong, guys. But you'll see rayleigh very basically almost always ubiquitously being used in like the hidden layers of like most neural network architectures, a lot of neural network architectures, and then you'll commonly see that softmax activation applied at the way end. But yeah, just quickly, just one sentence, one reason why we use rayleigh. Someone please.
Or you can name like what problem does it solve.
Yeah, there was like a kind of buzzword that it helps solve.
I think it was called like the disappearing gradient. How
Yeah, vanishing gradient. Yeah.
vanishing.
Yeah, so I guess we'll just, so like the problem is if you guys refer back to workshop 2, right, when we discussed the backprop equations, you guys can see at one point we're multiplying by the derivative of the sigmoid, right? So the sigmoid function has its derivative values are like very low, right? They're gonna range between like 0 and 0.25 ish, and like towards the ends, towards the left and the right, the sigmoid function is very flat, right? Which means the derivative is like very close to 0 at those endpoints. So that makes it really hard because when we're multiplying by a value that's almost 0 when we're doing backpropagation, that's gonna kind of lead to a bunch of gradients that are going to be like very close to 0 or just like underflowing straight down to 0. So we use rayleigh basically because it has a more consistent derivative. So it prevents us from, it kind of helps with that vanishing gradient problem of multiplying by like very, very low values. Okay, and then why does max pooling perform better than average pooling? I know at least one of you guys knows why. Come on. It's like 10 minutes ago. The faster we answer, the faster we can go to the next workshop.
It identifies the strongest features.
Yeah, so it kind of, yeah. It kind of forces us to be very decisive about what we're choosing. Yeah, so I'm sure you guys already know that. We spent a lot of time talking about that. So I think we can go to the next workshop, guys.
Yeah, so this is kind of brief. If you want like more formal and more like complete answers, just check this link. It's in the slides. Before we do that, do you guys have any questions about any of the material in here?
I asked a question in the chat, but like in the AlexNet structure, what is the norm, like 1, norm 2?
Awesome. So let's go back to that. So norm 1, norm 2, the 1 and the 2 have no real meaning, but normalization is just when you take your data and you try and push it into a particular range. So a common example of this would be pushing your data into like a 0 mean unit variance distribution, if we're assuming like a normal distribution. So we're just taking our data and we're scaling it down. So it's easier to manipulate and work with. And again, this isn't unique to convolutional neural nets, but it's just common practice in all of machine learning.
Yeah, it kind of, once again, kind of prevents values from exploding to extremely large values or like leveling down to 0. That's why you kind of perform batch normalization periodically. It just kind of keeps your data values in check, because really the information we really care about is like the value, how the values scale relative to one another, not so much what their like absolute values are all the time. Yeah, so it kind of just keeps our values in check.
Great question. Anything else before we move on?
Yeah, I have a quick question, and it's in a slide with the animation, I think, like really early into.
Sure, let's try and get back to that.
Yeah, so I remember that you said that the RGB, like how they convert the input volume into a single two-dimensional output is by like sometimes using an average and sometimes using other means. So what would be the method in this case?
Sorry, we're just trying to get back to it. Let's look at maybe this one.
Yeah,
that's right.
Okay, so in this case, we're just simply like adding them.
Yeah, so it's I guess I can see where you're getting the average from, but it's like a weighted average. So each of those red pixel or red boxes are multiplied by the those blue boxes on the left side, right? So wherever it's moving across, and then every part that's highlighted, it multiplies against the numbers in the red box and adds all of them together to get a single value that's output in the green box.
Yeah, so this is basically averaging it, right? You just don't divide it by 3 at the end. You're just adding them.
Yeah.
So I think it's the most common thing. Yeah, I guess. Yeah, you probably won't divide it by 3 just because it's better. I mean, it doesn't really matter, but
So it's a weighted sum. Sorry, not weighted average.
yeah,
my bad.
It's a weighted sum. You just add all of them together. I think that's like in the most standard case, like you just add them. Yeah.
Yeah, if you were to multiply by a constant, then yeah, it's just a constant scaling factor to
Yeah,
everything.
it doesn't matter.
It doesn't do anything. Yeah.
Great question.
Yeah, thanks for asking. I really like this slide. I feel like we should use it more often too.
This slide is so. If you guys like are ever 20 years from now, if you forget how a CNN works, just go to this slide and it'll all come back to you.
Yeah, I wish we wrote down where we got it from. I think this was from before I worked on these slides too.
Yeah. Anyway,
So,
I think we should go to the second.
Yeah, let's go to the second
let's
slides.
move on.
I have
Again,
the
if you
link.
guys,
oh, yeah, go ahead.
If you guys have any questions, just put them in chat.
Yeah, so I have the next slides in the chat right now, and then I'm going to share my screen. We're going to move straight on to This one. There we go. Straight into the second workshop, or the one that was scheduled for today.
And just a quick note before we move on, there is a feedback form again. Some of you have filled it out from when we first started it. If you guys haven't, please go back and just fill that out so we can help improve our content.
Yeah, I mean, the feedback form is the same form. It just asks you what workshop. Like you guys have seen it, so.
Or if you haven't, please try giving us feedback.
Yes.
All right, let's get started because we are running out of time. For part 2 of our convolutional neural networks workshop. The first part is actually going to be a little bit of a review, so I'm just going to kind of speed through that. But then we're going to go into advanced convolutional neural network architectures, things like inception net, ResNet, and UNet. We're just going to touch on it at a high level and talk about the advancements they've made compared to like what we've seen so far with convolutional neural networks. Then we'll talk about like miscellaneous topics like pre-training and transfer learning that might be a little bit more useful for the 2-week project that you go into in a couple weeks, actually. All right, so first off, a short history of convolutional neural networks. This is adapted from an article called Illustrated 10 Convolutional Neural Networks. It explains a lot of this in a lot more detail if you're interested, but we're going to go straight through it. So first off, we have LearnNet 5. This was the first, or I don't know if it was a first one, but it was the one that popularized convolutional neural networks, or the basic architecture of it. It introduced concepts like convolutions and pooling. And then in 2012 was when it really took off with Microsoft's AlexNet, which is what we just talked about, where it added deeper layers. So there's more layers and also more filters per layer. And also introduced rayleigh activation, which was faster to train because the gradient was really simple to calculate, right? The gradient was just 1 since it's a line, and 0 when it's below 0. And these are the review slides, so I'm just going to skip through them. But if you recall, we also had pooling. And then actually this slide has a nice diagram here that shows how the derivative is really simple for rayleigh. The top graph here is the rayleigh function, but then the bottom is the derivative of rayleigh, where below 0, it's 0, and above 0, the derivative is just 1. So when we do backpropagation, the rayleigh function doesn't really contribute much to or doesn't change the derivative much. It doesn't scale it down and cause a vanishing gradient like sigmoid might do that. Right, so with GoogleNet and Inception, this was the winner of the ILSVRC 2014 competition. It was a image classification competition, and the innovation that they introduced was the concept of inception modules. So up until this point, we've sort of like looked at layers in discrete, or we looked at a single neuron first, right? When we talked about logistic regression, when we first introduced neural networks. But then once we got into fully connected networks, we kind of bundled together those neurons into discrete layers so that we could kind of reason about them as a single unit. And then with convolutional neural networks, we kind of just stuck with that same model, but we introduced different kinds of layers like convolution layers, max pooling, rayleigh. And now with Inception, we're introducing modules. So modules are groups of layers that are bundled together. And within each model, there are parallel filters with different sizes that detect different size features. I think one of the things that we mentioned when we first talked about convolutional neural networks was that they are more robust against translations. And if you have a data set with images like rotated, then it's also robust against like rotations. But it's not really great at detecting features that are different sizes. Like if a person is like up against the camera, they're a lot larger, but you can still recognize that they're a person. Versus if the person was standing way far away in the background, you can still recognize it's a person, but a filter is a fixed size, like a 3x3 or 5x5. With Inception, the way they solve that is, oh yeah, here's an example of those images. Here's a dog up close and a dog lots further away, and a dog like further up and further away. The number of pixels that the dog occupies is different, but you've all recognized that it's the same kind of dog. And the way that Inception addresses this is that they have not only does one layer have like convolutions that are of a fixed size, right? A filter of a 3x3 or 5x5, but you actually have multiple layers in parallel. So you have 1x1 convolutions, 3x3, 5x5, and then also 3x3 max pooling. But the way this works is that like the 5x5 convolutions might be able to detect features that are larger in scale. So like the close-up dog in the previous slide might look might be detected by the 5x5 filters, whereas the ones that are further away might be detected by the 1x1 or 3x3 filters. And then there's also 1x1 convolutions, which kind of sounds a little weird, right? Like, why do you want a convolution that has or a filter that's only 1x1? The whole idea behind filters is that we're able to learn we're able to learn relationships that are relationships between pixels that are close together, right? There's a certain spatial locality to these images that we're taking advantage of when we're doing convolutions. And if we're doing 1x1 convolutions, we're not looking at any adjacent pixels. We're only looking at a single pixel. So what's the advantage of doing that? The problem is that large kernels, or which were introduced by Inception, right? We have a lot of parallel layers with different size kernels, and larger kernels like 3x3 and 5x5. They're expensive if you have the input volume with a very large depth. So in the diagram from the previous workshop, we saw that a filter is not only like 5x5, but it's 5x5 by the depth of the input, right? So that's how many weights it has to train for that specific filter. So the example is if the previous layer is an output with a depth 256 and the current layer has a 5x5 filter with 256 kernels, then there's 5x5 by 256 by 256 total weights, right? Because the output, that's supposed to be a input volume of depth 256. So the input volume is depth 256. The filter has dimensions 5x5. So you have 256 times 5 times 5. And then you have 256 neurons. So you multiply that by 256, and that's a large number of filters.
Yeah, and can I? There's something I want to address about that. So I feel like the natural question that some of you guys might be asking right now in your head is like, wait, I thought like the depth is gonna be 3 because there's like R, G, and B. That's true for like the original image, right? But keep in mind what we usually end up doing, like you guys just saw with AlexNet, right? So you take the input, you pass that through a convolution, you max pool that, and then you throw that max pooled result into another convolutional layer, so on and so forth, right? So remember, like, let's say in the first layer, we have like 500 features, right? Then your depth of that convolutional layer is like 500, right? And then when you max pool it, it's still 500. Now you're throwing something with a depth of like 500 into another convolutional layer, as opposed to something with a depth of 3, like your original input image, right? So that's just kind of how, like, if you guys were confused, like, well, how do I have a depth that's like 256? That's kind of why that happens.
Mm-hmm. Also, another thing I wanted to note is that the input doesn't necessarily have to be like RGB or it doesn't have to have like 3 channels or 1 channel if it's monochrome. You can also have more channels in that, right? If you, for example, have a scanner that or like you have an infrared image and also you have an image that's taken in ultraviolet or in other different energies. Those can also be, you can also input that, or you can also layer that into a volume, right? And you'd have a volume that has different dimensions than just RGB 3 channels. So we've been working with 3 channels because that's pretty much what most images are like, but it's not necessarily the case. All right. I know I've been kind of going fast through this, but how is everything going? Do these concepts make sense? Am I going too fast? Because I can slow down. I think we do have time next workshop that we can eat into if we don't get through all of this today. Let me open the chat so I can see. I think I missed how the kernels are generated. Okay. Yeah, I think I'm gonna actually bring up that diagram again because that was really helpful for explaining. Let me open up the image. Okay.
I think the kernel is just another word for filter, right?
Yes, that
Yeah.
is right.
I think that might have been what the question was referring.
Oh, okay. Yes. Sorry. So wait, was that your question actually, Trevor? Was your question like what confusing between kernels and filters? Or were you confused about where the weights are coming from, or like how I got the number of like 5 times 5 times 256? Because I know, Samuel, you're confused by why I multiplied by 256 twice. So this is a typo here. Am I sharing my right screen? I can't see what I'm sharing.
You're on AlexNet.
Right, okay, great. So I want to actually go back to this, or the diagram where we had
the numbers of each filter matrix are the weights. Yeah, that's correct. So those are the learned parameters, right?
Yes. So everything in this red box here are the weights, and the depth comes from 3 by 3 by the number of or the depth of the input volume, right? So it's the dimensions of the filter, which is 3 times 3, the depth of the input volume, which is 3 in this case, so it's 3 times 3 times 3, and then the number of filters in this case is 2. So you have 2 times 3 times 3 times 3. In the example I gave in the second set of slides, I did 5 by 5 filters with 256 filters and the input volume with a depth 256. That's how I got 5 times 5 times 256 times 256. Does that make sense now?
Yeah, so there's 256 filters, and the depth of the input is also 256. So the 256s are two different 256s.
Exactly. Yeah, that's my bad for using the same number. They should be different. Oh. Okay, great. Looks like we're on the same page. Does anyone else have any questions? Yeah, your questions are really helpful for like catching things that aren't clear when I first make the slides. So please keep asking and interrupting if you can. I'm going to go back to our slides now. Okay, great. So dimension reduction. What the one-by-one convolutions do is that they map a single column, one of the depth columns, into a single, I guess, pixel or voxel of the output. So in this sense, we're kind of compressing the depth of the input to so like if our input was of depth 256, we're going to reduce that depth, compress it into something like 64 in this case, in this example. So in this first example, we did a 256 input, 256 kernels, and they're 5 by 5 kernels. So we have a total of like 1,600,000 weights. If we used a 1 by 1 convolution in between, what we're going to do is take a 256 input depth, pass it through 64 1 by 1 kernels, and that will output the same dimensions, except that instead of the depth being 256, the depth is only 64 since we have 64 kernels, right? And then when we multiply it by the 256 5 by 5 kernels, we only have a fraction of the number of weights that we need to train. That's including the 64 1 by 1 kernels, which is 400,000 compared to 1,600,000.
So you can think of it as like convolving over the depth axis instead of like the plane axis. Because you're
I don't-
compressing, because you're compressing down the depth of the input.
Yeah, I would be afraid of. I don't want to say convolving
Yeah, not
because
convolve's probably not
yeah,
the correct word, but
convolving is not the correct word because we're not like moving a filter through it. It's taking a weighted sum of the entire column, now entire depth. And what it's kind of doing is it's the same idea as the convolution layers, where we're kind of reducing the size, or max pooling, where we're reducing the dimensions, or the width and height. When we reduce the width and height, we're kind of compressing the image. We're reducing it to just essential information that's necessary for making our predictions. In this sense, we're compressing it, but instead of compressing the width and the height, we're compressing the depth. So we might have 256 kernels that are detecting different things like diagonal lines, vertical lines, horizontal lines, but all of that information might not be necessary for like the next layer to make a good prediction. So by passing it through a 1-by-1 convolution, we're reducing the depth. So that 1-by-1 layer is going to take a look at all 256 kernels, that 256 feature maps, and it's going to compress that information into 64 layers instead. What, 64 5x5 kernels instead of yeah, actually it would work as well. You could do 64 5x5 kernels as well, and it will do essentially the same thing. The reason we're doing 1-by-1 kernels instead of 5x5 is because we're not trying to learn any relationships between adjacent pixels. We're just trying to compress the information. So in this sense, the layer is doing only one job that's independent from the layer that comes after it, the 256 5x5 kernels. Because sometimes we want like more of those 5x5 kernels so we can learn different kinds of features. Like one might learn diagonal lines, or if you're going higher up or deeper into the network, you might learn higher level features like, oh, this kernel is learning a circle shape, or it might learn a circle shape with a cross through it or something like that. And so having more kernels gives us more freedom in that sense. But we still want to be able to compress it. So we have that 1-by-1 kernel separate, or 1-by-1 layer separate. All right, I think we can move on. The next step is ResNet. So after AlexNet, or no, not AlexNet, this is Inception Net, right? Won the 2014 competition. ResNet came along, and this is even more recent. One intuition, or one thing, or it's solving an interesting problem, which is that when we have deeper neural networks, typically we'd expect them to perform better, right? And the reason we think they would perform better is, or I'll go into that in the next slide. But what happened is when we added more layers, they actually started to perform worse, which is kind of counterintuitive because a neural network with more layers should be like a superset of a neural network with fewer layers, right? So why would it perform better? And I'm talking about the training error too. So if you look at this graph, the training error of the 56 layer network was higher than the training error of the 20 layer network. So from this, we can tell that it's not because of overfitting, right? Because if it was overfitting, what would we see? Can you guys guess? Like, what would these two graphs be? So this is the graph of training error, and this is the graph for test error. If this was because of overfitting, like if adding more layers caused us to overfit, what would these graphs look like? The error goes up at the end. Oh, but which one? You're kind of on the right track, Trevor. The error goes up at the end, but which does the test error go up or the training error go up? Oh, Samuel also answered, training is lower, test is higher. Yes, that's exactly right. So what you'd see is the training error goes down and kind of settles at like a minimum. And the test error is also going to go down, but at some point, at some iteration, it's going to start to go back up as well. So that's characteristic of overfitting. But ResNet, or what the developers of ResNet found, was that when they added more layers, not only was the training error consistently higher than a network with fewer layers, the test error, or not only was the training error consistently higher, did I say that wrong? Not only was the test error consistently higher, but the training error was also consistently higher as well. Darren, yeah, that's exactly the right answer. The training error increases, or the test error increases, and the training error decreases. Sorry, I'm kind of like flipping these around often, but this is basically, or this is what they call the degradation problem. And the reason we'd expect the neural network with more layers to perform better than the neural network with fewer layers is that if we had a shallow neural network like the one on the left here, where we only had 2 hidden layers, and then we added a 3rd layer, why would we expect it to perform better? Why do you think that this would perform better than the shallow neural network? I think we gave a couple answers before. I mean, you can also throw out some guesses.
Yeah, there's like basically like an infinite number of ways to
Yeah.
kind of justify this. So yeah, go ahead. Like we've discussed this in the past, right? Like, can someone kind of give their intuition for it?
Actually, like if we were training this, let's take an extreme case. If we set all of this, or if these 2 networks were identical, like the first layer was identical, the second layer was identical, and then we added a 3rd layer, what would the 3rd layer have to do in order to perform almost exactly the same, or exactly the same as the network without the 3rd layer?
It's not a trick question.
Yeah, there's a lot of good answers for this, but yeah. All right, for the sake of time, I'm just gonna give an answer. But like, we can assume like the hidden layer, the 3rd hidden layer that we're adding, is just gonna be like the identity function, right? It doesn't change anything at all. And if we assume that's the case, then essentially these 2 networks would be identical, right? If the 3rd layer is the identity function, it doesn't change anything. Then when we forward propagate, then the result is going to be exactly the same as the shallow network. But what we find is, so in theory, that's what it should perform the same. But in practice, what happens is that the extra layers seem to have trouble learning this identity mapping. Instead, it has a lot easier time learning a 0 mapping. And intuitively, and one way you can think of it is that when we're doing regularization, what we're doing is we're trying to push those weights down to 0. Or like if we didn't talk in depth about L1 and L2 regularization. That's something that's I think mentioned in beginner track. But essentially those forms of regularization push the weights to 0. They prefer networks that have lower weights, and networks with smaller weights are typically simpler or less complex, and they also generalize better. That's why we do that kind of regularization. But when we're adding more layers like this, we actually wanted to learn an identity mapping by default instead of a 0 mapping by default. Because if we learn a 0 mapping, then it's not going to perform that well. Whereas if it learned identity mapping, in the worst case scenario, it's going to perform at least as well as a shallow network. And that's what the residual block, or with that in ResNet, tries to address. So the residual block adds an alternative path. So this is forward propagating. So this is like the previous layers, or the input. It goes into a weight layer, or like a convolution layer, or a fully connected layer. Goes through that rayleigh activation function, and then maybe another convolution or fully connected layer. And instead of just being outputted to the next layer, what it does is it also takes the input, the original input, and adds it to the function. So if these weight layers, the f of x learns the zero function, then f of x plus x is going to be x, which is the identity function. So when we use regularization like L1, L2, and those regularization methods push our weights to zero, we're not going to end up with a zero function. Instead, we're going to end up by default with an identity function, and that's going to that's what we want, right? So in the worst case scenario, it will default to being at least as good as a shallower neural network. Yeah. And now Justin will take it from here, talking about classification, detection, and segmentation.
Sure. Ben, do you want to continue to share, or?
Whatever you prefer. Yeah, sure.
Okay. So we're just gonna go into different problem spaces concerning CNNs and like what they're most applied toward, and like kind of discuss the differences. Okay, so classification, we're trying to answer the question, what is this image of? So basically we're trying to label this image. So I think if we progress, there might be a, yeah, so in this image, we get our network to label this as a dog. So good job. Detection localization, we're trying to answer where are the objects in this image. So we're trying to label different regions of an image. So we make a little bounding box. So we have like a localization of where a dog might be. Lastly, we have a segmentation. So which pixels does the object occupy? So we're labeling particular pixels within an image. So here we see a binary segmentation, not dog and then dog. So there's a little bit of a difference between different types of segmentation. So there's regular semantic segmentation. So this is kind of like a classifying thing. So we see like there's a puffin and then another puffin and then another one. And then everything outside of those pixels will be not a puffin. And there's also instance segmentation. So we're trying to label and distinguish multiple instances of a particular class. So we have puffin 1, puffin 2, and puffin 3. So one such architecture that does this is on the next slide. So the UNet architecture. So this is particularly used for segmentation tasks. So if we just read this diagram, we can see these blue arrows represent just convolutional layers and an activation function. And as we drop down, we're doing downsampling that we've seen, like max pooling. So we continue this and we get to like a very baseline representation of our input data. And then we kind of map that all the way up into an output of like a segmentation map. So we see like a characteristic U that forms in the model. So again, we're downsampling and bringing back up. It's like a common theme in machine learning. So another technique that they use is transposed convolution. So their convolutions and pooling reduces the width and height, but how do we like from that bottom of the U that we've seen, how do we bring that back up into our original input space? Like, how do we get it back to a form where we can meaningfully make segmentation? So if we move on to an example, we see this transposed convolution. So we have a 2x2 input, 1, 2, 3, 4, and we have a kernel. So think of this as like a filter, but in reverse. So what we're going to do is we're going to take, let's say the index 1, 1 of our input matrix, and we're going to scale our kernel by the particular element that it corresponds to. And then we're going to put that output and just plop it into our final result. So if we track the upper kind of track, we see 1 times our kernel will just give us the kernel back. And we just plot that into a 3x3 matrix. 2 times our kernel in the second track, 2 times our kernel will give us this output, and then we just plot that in and we add it to whatever else was originally in there. And then we continue to do this for every element within our original matrix. And then we get a final result that is a greater dimensionality than we had started with. So that's kind of the intuition, and that's the mechanism behind this, like bringing back up from a particular latent space.
Yeah, this is, Justin mentioned, like this is extremely common theme in machine learning models. Like I think if you guys take Advanced Plus Plus next quarter, I think we're offering it. I think Ben, we discuss a lot of kind of models and whatnot that kind of use this kind of idea.
Yeah, you will see some stuff like variational autoencoders do the same thing.
Yeah. Yeah, that's a very canonical example of kind of extracting a lot of rich information from some input space and then upsampling that rich information into some kind of output.
Awesome. So I think we can move on from this slide unless there are any questions on this.
I mean,
Okay.
I think we can kind of just stop here and take questions. We have only a few minutes left, unless you guys want to try to get a few more slides in.
What about, actually, let's ask you guys.
Yeah, are there questions? If there are, then we can stop right here.
Yeah, do you guys want us to move on, or you want to, if you have questions, please ask now. Yeah. We have, it looks like,
I think we have like 3 or 4 more slides. Yeah.
Yeah.
If you guys don't mind, we'll just push on for a little bit. Hang in there. So the next topic we're going to go into is something called copy and crop. So that successive downsampling of our input space is called, and we are effectively encoding our input into a lower dimensional space, like that is like really dense, full of information. So that's an encoding. So we compress our original image into a latent space, and then we use this transpose convolution to upscale back into our original dimension. So we lose some sort of knowledge of like where the image and the information comes from. So if you guys think about max pooling, like it didn't have any sort of indicator for where in a particular local field, like we're getting our max value from. But by concatenating the output of previously higher layers, like we can recover some of that location information. So we can kind of piece back together when we upscale it, like where in our original image a particular instance of a object was. So some miscellaneous topics. So another thing that's very common in CNN. So the training process for CNN is super intensive. So very time consuming, and it requires a lot of training data. So the solution to this is we use a pre-trained model on a different data set as a starting point. So instead of, so we're essentially trying to transfer the knowledge from a already trained network to apply to a new problem statement. So some different methods of transfer learning on the next slide. So pre-training and fine-tuning, we train a model on a particular data set and then use those final weights. So all of those filters, like all of those, like that big volume of filters, we're going to be using all of those values as the initial weights for our new model training. We can also just extract like a whole convolutional part of a CNN and just freeze all of those layers, just pick that up and then place that into our new model. And then we're just going to be training our vanilla neural network to optimize toward our use case.
Yeah, so let's say like let's say in the literature there's some like paper where someone devises some neural network that has like X accuracy on like some like task of like training of like classifying dogs or something. And then like maybe you want to like also classify like dogs, but maybe like you want to like classify like certain types of dogs or something like that. You want to maybe make your problem more specific or maybe an extension off of that problem. So you know that the kind of space that the function that other researchers model resides in is already kind of close to where you want to be, right? So it's probably a good idea to start there instead of just randomly initializing, right? Because if you start somewhere where you know you're closer to the correct answer, you're gonna need less data than if you just like start from scratch completely, right? And then what Justin was saying about like freezing layers. So let's say if you want to do like something more complicated than just classifying if it's a dog, like if you want a certain type of dog, you're probably going to need like a bit more of a complex network. Maybe like you're going to need some extra layers or whatnot. So maybe you can take that like network that's already there and use that and like plop it into like the middle of your network for your new one, because maybe you're going to append some like new layers towards the end of it or to the beginning of it. So that neural network kind of becomes a subset of your greater neural network.
Awesome. So on the next slide, we actually have a couple of questions for you guys, but in the spirit of just trying to keep it in time, we're going to leave this to the next workshop and kind of do a similar review, like a revision of this week's workshop next week, just to get you guys back in that kind of mindset. So that'll conclude all of the new content for today. I'm dropping the feedback form in the chat. So if you guys have a chance, please fill that out. I know we kind of rushed through that last part. So again, we're going to review a lot of the material, so don't worry too much about it.
Yeah. Thanks for sticking around. We really appreciate it, especially during midterms.
Once again, like this workshop, the second one that we kind of just went over is supposed to be like a very kind of heuristic, like overviewy kind of introduction to like some more advanced topics. Like for the down sampling to up sampling thing, like we're not really gonna like talk about like, well, like how do you generate those upsampling filters and whatnot. Like don't really worry about that. We're just trying to like get you guys to kind of like dip your toes in like some like other more advanced topics just to get some exposure to it. So like we did go pretty fast through it, but like it was also like meant to like not be as dense. Like the information was not meant to be as dense for the second workshop.
We kind of just wanted to let you know that these things existed and that you could learn more about them if you're interested, but we don't really have time in this workshop series to go into real detail about them. So hopefully, now you're aware that there's the difference between segmentation, classification, detection, that you can look up like, oh, I need to do this specific task, and you know what you look for now. Whereas we just talked about classifiers before this point.
Yes, so we'll be here until you all leave. So if you guys
please ask any questions too.
So please like ask your questions, and if you don't have any, feel free to hop off, and see you guys next week, where we're going to talk about recurrent neural networks, which is another very applicable area.
And then after that, we'll go into PyTorch, and then finally we'll start our project. We're gonna get more practical, I promise.
Yeah, we're almost to the super practical, like how do I actually implement stuff part.
And once again, we really appreciate your guys' support and coming out.
Yeah, of course.
Thanks, guys.
Yeah, of course.
Thanks for coming.
I'm gonna stop the recording now. So yeah. Thank you all for coming up.